The electron has mass. You can measure it. You can calculate it. It resists when you push it. It bends when gravity pulls. And yet, as far as our most powerful experiments can determine, the electron has no physical size. No width, no volume, no internal structure of any kind. It behaves as though it occupies no space at all. Think about that for a moment. How can something have mass, real, measurable mass, without having any detectable size? In your everyday experience, mass and size always go together. Heavier things tend to be bigger. A bowling ball has more mass than a marble because there is more material packed into a larger volume. But at the deepest level of reality, this connection completely breaks down. Fundamental particles carry mass without having measurable dimensions. And the reason why is one of the most profound discoveries in all of physics. If you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Pick up a rock. Feel its weight in your hand. Now pick up a bigger rock, a heavier one. You notice immediately that it takes more effort to lift. It resists your muscles more stubbornly. If you try to throw it, you would have to push harder to get it moving. In your everyday experience, this relationship between mass and physical size is so reliable that you never even think about it. Heavier things tend to be bigger. A bowling ball has more mass than a golf ball. A truck has more mass than a bicycle. A shipping container has more mass than a shoebox. An elephant has more mass than a mouse. The connection between how much something weighs and how much space it takes up seems completely natural, almost obvious, so deeply embedded in your experience that questioning it feels absurd. When you pick up a heavy object, you feel the weight of material packed into a volume. A brick of lead is heavy because a dense, tightly packed substance fills that rectangular space. A hollow plastic ball is light because there is almost nothing inside. A solid iron cannonball is heavier than a wooden ball the same size because the iron atoms are more massive and packed more closely together. You learned these relationships as a child, long before you knew any physics, simply by interacting with the world. Heavy things are big, light things are small. More stuff means more mass. No stuff means no mass. It seems like an unbreakable law of the universe. This intuition is not just casual. It shaped how scientists thought about matter for centuries. When humans first began asking what everything is made of, they naturally assumed there must be tiny pieces of material at the very bottom. The world we see is made of smaller things. Those smaller things are made of even smaller things. And at each level, the mass of the larger object would come from the combined mass of all its tiny parts, like how the weight of a bag of marbles comes from adding up the weight of every marble in the bag. This picture is tidy, intuitive, and deeply satisfying. It tells you that mass is simple. Mass is just stuff. Count the pieces, weigh the pieces, and you know what the total mass is. This idea has ancient roots. Around 400 BC, the Greek philosopher Democritus proposed that all matter is made of tiny, indivisible particles. He called them atomos, from the Greek word meaning uncuttable. Democritus imagined that if you took a piece of gold and kept cutting it in half, again and again and again, you would eventually reach a piece so small it could not be cut any further. That final piece would be an atom of gold. His teacher Leucippus had developed similar ideas. In their view, atoms were tiny, solid objects. They had definite shapes, definite sizes, and definite masses. They occupied space. They were physical things that you could in principle hold in your hand if your hand were small enough. And the mass of a large object came from the combined mass of all its tiny atoms, each one contributing its share to the total weight. But Aristotle rejected this idea entirely. He believed matter was continuous and infinitely divisible. You could always cut smaller. There was no bottom, no final particle, no smallest unit. For nearly 2,000 years, Aristotle's view dominated Western thought. Atomism was considered an interesting philosophical curiosity, but nothing more. Nobody could prove atoms existed. Nobody could see them or measure them. The idea remained a speculation without evidence. Then, the early 1800s changed everything. The English chemist John Dalton revived the atomic idea, and this time he brought hard evidence. Dalton noticed that when chemical elements combine to form compounds, they always combine in fixed ratios by mass. Hydrogen and oxygen always form water in the same proportions. 8 grams of oxygen always combine with 1 gram of hydrogen. Carbon and oxygen always form carbon dioxide in fixed proportions. Every chemical reaction obeyed this rule, and this pattern made perfect sense if matter was built from atoms with specific, unchangeable masses. If a water molecule always contains 2 hydrogen atoms and 1 oxygen atom, and if an oxygen atom is 16 times heavier than a hydrogen atom, then you would always need 8 times more oxygen by mass than hydrogen to form water. The ratios are fixed because the atoms are fixed. Dalton's atomic theory transformed chemistry from a descriptive art into a predictive science. Atoms became working tools. But even then, nobody knew what an atom actually looked like, or whether it had any internal structure. Most scientists pictured atoms as tiny, solid, featureless spheres. Indivisible. Fundamental. With their mass being simply the inherent weight of the particle itself. Small, solid, heavy. Nothing inside, nothing smaller underneath. That was supposed to be the end of the story. That assumption held for about a century before it shattered. In 1897, the British physicist J. Thomson discovered the electron. He was working in the Cavendish laboratory at Cambridge, studying cathode rays, mysterious beams of something emitted from negatively charged electrodes inside vacuum tubes. These glass tubes had most of their air pumped out, creating a near vacuum inside. When a high voltage was applied across the tube, something streamed from the negative electrode, the cathode, toward the positive electrode, the anode. Whatever this something was, it made the glass at the far end of the tube glow with a faint greenish light. It cast shadows when objects were placed in its path. It could spin a tiny paddle wheel, suggesting it carried momentum. But nobody knew what cathode rays actually were. Some physicists thought they were waves, like light. Others suspected they were particles. Thomson settled the question with a series of elegant experiments. By carefully measuring how electric and magnetic fields deflected these beams, he showed they were made of particles. Tiny, fast-moving particles that carried a negative electric charge. And he measured something remarkable about them. Their ratio of charge to mass was enormous, far larger than for any known ion or atom. This meant either the particles carried a very large charge, or they had a very small mass, or both. Thomson concluded they were extremely light, far lighter than even the lightest atom, hydrogen. And crucially, these particles were identical regardless of what material the cathode was made from. Whether the electrode was aluminum, iron, platinum, or any other metal, the same tiny negative particles came streaming out. Thomson realized something revolutionary. These particles were not atoms. They were coming from inside atoms. Atoms were not indivisible after all. They had internal parts. They contained smaller things. This was the first crack in the ancient picture. There was structure inside the atom. The mass of the atom was not the mass of one indivisible lump. It was distributed among internal components. Thomson proposed a model of the atom as a sphere of positive charge with electrons embedded in it, like raisins scattered through a pudding. The atom's mass came partly from the electrons and partly from the positively charged material they sat in. Once again, mass came from the stuff inside. Then came Ernest Rutherford, and the picture shattered yet again. In 1911, Rutherford, along with Hans Geiger and Ernest Marsden, set up one of the most important experiments in the history of science. They fired alpha particles, which are helium nuclei, at an extremely thin sheet of gold foil. The foil was astonishingly thin, only about 1,000 atoms thick. Alpha particles are relatively heavy, roughly 7,000 times the mass of an electron, and they move at tremendous speed, roughly 5% of the speed of light. According to Thomson's model, where positive charge and mass are spread uniformly throughout the atom, the alpha particles should have passed through the gold foil with only very slight deflections. A diffuse cloud of positive charge would barely nudge the incoming projectiles. It would be like firing bullets through a bank of fog. The bullets would pass through with barely a wobble. And most of the alpha particles did pass straight through, exactly as expected. Geiger and Marsden sat in a darkened room, watching a fluorescent screen for tiny flashes of light that appeared whenever an alpha particle struck it. Hour after hour, they recorded flashes, noting the angle at which each alpha particle arrived. The vast majority came through at small angles, just as Thomson's model predicted. But then something happened that nobody predicted. Some alpha particles bounced back at steep angles. A few bounced almost straight backward, as though they had struck something incredibly dense and hard inside the atom. The flashes appeared on the wrong side of the foil, behind where the alpha particles had been fired from. Rutherford was stunned. He later said it was as astonishing as if you had fired an artillery shell at a piece of tissue paper, and the shell came back and hit you. This result made no sense unless almost all the atom's mass and positive charge were concentrated in a tiny, extraordinarily dense core. Rutherford had discovered the nucleus. The atom was not a uniform sphere of material, it was overwhelmingly empty space. A tiny nucleus, about 10,000 times smaller than the atom itself, sat at the center, and lightweight electrons orbited at comparatively enormous distances. If you scaled an atom up to the size of a football stadium, the nucleus would be about the size of a pea at the center of the field. The stands, the walls, the roof, the entire structure, all empty. Just a pea at the 50-yard line, and a few electrons orbiting somewhere out near the parking lot. And once again, the pattern held perfectly. Where did the atom's mass come from? From the stuff inside. Almost all of it sat in that tiny nucleus. The electrons contributed less than 0.1%. Over the following decades, scientists discovered that the nucleus contains protons and neutrons, collectively called nucleons. Protons carry positive charge. Neutrons carry no charge. Both have roughly the same mass, and the mass of any nucleus was simply the combined mass of all its protons and neutrons added together. Heavier elements had more nucleons. Lighter elements had fewer. Mass came from counting and weighing the parts inside. For a while, protons and neutrons seemed to be the final answer, the fundamental building blocks, the bottom of the nesting doll. Their masses were well measured. A proton has a mass of about 1.67 times 10 to the negative 27 kilograms. A neutron is slightly heavier, and the mass of every atom in the universe could be accounted for by tallying up its protons and neutrons and adding their individual masses together. Simple and satisfying. But nature was not finished. In the 1960s and 70s, physicists performing high-energy scattering experiments discovered that protons and neutrons are not fundamental either. They have internal structure. Each proton contains 3 smaller particles called quarks, specifically 2 up quarks and 1 down quark. Each neutron also contains 3 quarks, 1 up and 2 down. These quarks are bound together by particles called gluons, which carry the strong nuclear force. The existence of quarks was proposed independently by Murray Gell-Mann and George Zweig in 1964 and confirmed experimentally over the following decade through deep inelastic scattering experiments at SLAC, the Stanford Linear Accelerator Center. The machine at SLAC was a marvel of engineering, a linear accelerator stretching 2 miles long beneath the hills of California. Inside this enormous tube, electrons were accelerated to energies so extreme that when they struck a proton target, they penetrated deep into the proton's interior rather than bouncing off its surface. Physicists observed patterns of deflection that only made sense if the proton contained smaller, hard, point-like objects inside. The electrons were bouncing off individual quarks within the proton. The scattering patterns revealed substructure clearly, unmistakably, and beyond any reasonable doubt. So once again, mass seemed to come from parts inside. A proton is massive because it contains quarks and the energy binding them together. A nucleus is massive because it contains protons and neutrons. An atom is massive because it contains its nucleus. A rock is heavy because it contains atoms. It is a nesting doll picture of reality, and at every level, mass comes from the accumulated mass and energy of the components within. This pattern is so consistent, so reliable, and so deeply embedded in the history of discovery that it creates an almost irresistible expectation. If every single time we opened something up, we found smaller things inside, then surely at the very bottom there must be some final, tiny thing. Some ultimate grain of material, some smallest possible speck of physical substance that simply has mass because it is a physical object with size and volume. Something solid, something dense, something that occupies space. Something you could, in principle, point to and say, there, that is where the mass lives. But this is exactly where nature breaks the pattern. And it breaks it in a way that challenges everything you think you know about what mass is. Consider the electron. The electron is one of the most precisely measured objects in all of science. Its mass is known to extraordinary accuracy, approximately 9.109 times 10 to the negative 31 kilograms. Its electric charge is known even more precisely. Its magnetic moment has been measured and confirmed to better than 1 part in a trillion, making the comparison between the measured value and the theoretical prediction one of the most precise agreements in the entire history of physics. We know more about the electron's properties than we know about virtually any other object in existence. And yet, despite more than a century of increasingly powerful experiments, nobody has ever detected any internal structure inside the electron. Nobody has found smaller parts within it. Nobody has measured any physical radius for it at all. As far as our most powerful experiments can determine, the electron has no spatial extent, no width, no diameter, no volume, no measurable cross-section. It behaves, in every experiment we have ever devised, as though it occupies no detectable space whatsoever. How do physicists actually know this? How do you measure the size of something so unimaginably small? The answer goes back to the same method Rutherford used, refined and amplified to staggering precision. You throw things at it and study what bounces back. This technique is called scattering, and it is the most powerful tool physicists have for probing the structure of matter at the smallest scales. The idea is beautifully straightforward. Fire a beam of particles at a target. If the target has internal structure, if it contains parts distributed across some physical volume, then the pattern of scattered particles will reveal that structure. Different arrangements of charge and mass inside the target produce different characteristic scattering patterns. By analysing how particles bounce off, you can reconstruct a picture of what the inside looks like, even when the target is far too small to see directly. Think of it like throwing tennis balls at an object hidden behind a curtain. If the object is a solid wall, the tennis balls bounce straight back. If it is a collection of posts, Some balls pass through the gaps, and others deflect off the posts. By studying the pattern of bouncing tennis balls, you can figure out the shape and arrangement of whatever is behind the curtain, without ever pulling the curtain aside. This is precisely how Rutherford discovered the nucleus. The deflection pattern of alpha particles bouncing off gold foil told him the atom's mass was concentrated in a tiny central core. The same method, scaled up enormously in energy, revealed the quarks inside the proton. Physicists at SLAC in the late 1960s fired extremely high-energy electrons at protons and observed scattering patterns that only made sense if the proton contained 3 hard, point-like objects inside. The electrons were deflecting off individual quarks within the proton, and the data left no room for doubt about what was inside. But to probe something even smaller, you need even higher energies. This is a consequence of quantum mechanics. Every particle has a wavelength associated with it, called its de Broglie wavelength, and that wavelength determines the smallest structures it can resolve. The higher the particle's energy, the shorter its wavelength, and the finer the details it can reveal. It is similar to how a magnifying glass can only show you details larger than the wavelength of visible light. If you want to see smaller structures, you need shorter wavelengths, which means ultraviolet light, X-rays, or electron beams. For probing subatomic structure, you need particles with wavelengths far shorter than the objects you are studying. And getting those short wavelengths means accelerating the particles to enormous energies. This is why particle physicists build accelerators. Enormous machines, some of them miles long or miles in circumference, designed to push particles to higher and higher energies. The higher the energy, the shorter the wavelength, and the smaller the structures you can see. Every generation of accelerators has probed deeper into matter, seeing finer and finer details. Accelerators in the 1950s revealed the internal structure of nuclei. Accelerators in the 1960s and 70s revealed quarks inside protons. And accelerators from the 1980s through the present day have searched for structure inside electrons and quarks, firing particles at these supposedly fundamental objects with energies that would have seemed inconceivable to earlier generations of physicists. Now here is the critical point. When you perform the same kind of experiment on the electron itself, when you fire other particles at it with higher and higher energies, probing smaller and smaller distance scales, you find nothing inside. No substructure, no hard internal core, no smaller components. The scattering patterns match exactly, precisely, perfectly what you would expect from a single, structureless point with no spatial extent. There is nothing to find inside the electron because, as far as these experiments can tell, there is nothing inside. Experiments at particle colliders like LEP at CERN, the Large Electron-Positron Collider, and subsequent measurements at the Large Hadron Collider have probed the electron's structure down to distance scales of roughly 10 to the negative 18 meters. That is a billionth of a meter. To put that in perspective, it is about 1,000 times smaller than a proton. And a proton is already so small that tens of thousands of them could sit side by side across the width of a single atom. We are talking about distances so unimaginably tiny that no analogy from daily life can do them justice. At these extraordinarily tiny distance scales, if the electron had any internal structure, any hidden components, any finite physical radius at all, the scattering experiments would reveal it. There would be deviations from the point-particle prediction. There would be anomalies, resonances, or subtle shifts in the data that indicate something is there, some spatial extent, some physical volume. Nothing has appeared. The data is clean. The electron scatters exactly as a structureless point should, and it does so at every energy scale we have ever tested. There is no hint of substructure, not at the scale of a proton, not at 1/100th of a proton, not at 1,000th of a proton. not at the smallest distances human technology has ever reached. The electron appears, by every available measurement, to have no measurable size. Every time physicists have built a more powerful accelerator, expecting that this time they might finally see something inside the electron, the answer has come back the same. Nothing. Just a point. Structureless, featureless, carrying mass and charge and spin, but occupying no detectable volume. And yet, the electron has mass. Real, measurable, physically consequential mass. It resists acceleration. When you apply a force to an electron, it does not respond instantly. It pushes back. It has inertia. It behaves exactly as a massive object should. If you place an electron in a penning trap, a device that uses precisely configured magnetic and electric fields to confine a single charged particle in a tiny region of space, you can measure its mass directly by observing how it moves. The trap holds the electron suspended, hovering in a vacuum, isolated from virtually everything. The electron orbits and oscillates within the trap's fields, and the frequency of those oscillations depends precisely on the electron's mass. By measuring those frequencies with extraordinary precision, you extract the mass. The physicist Hans Democritus pioneered this technique in the 1970s and 80s, isolating single electrons for weeks or months at a time. Imagine that. A single electron, one solitary particle, held in place and studied for weeks. Democritus measured the electron's properties with a precision that stunned the physics community. His work, along with similar efforts by other researchers, nailed down the electron's mass and magnetic moment to accuracies that remain among the most precise measurements humans have ever made of anything. The electron's mass is not theoretical. It is not inferred. It is directly observed in experiment after experiment. It affects how electrons orbit atomic nuclei, how they scatter off other particles, how they accelerate in electric fields, how they emit and absorb photons. The electron's mass is as real as the mass of a bowling ball. There is no ambiguity. But where does that mass come from? In the old nesting doll picture, mass always came from the stuff inside. The rock's mass came from its atoms. The atom's mass came from its nucleus. The nucleus's mass came from its protons and neutrons. The proton's mass came from its quarks and the energy binding them. But the electron has no stuff inside. There are no smaller parts to add up. There is no internal material whose weight you could sum together. The electron's mass does not come from the combined mass of hidden internal components, because, as far as any experiment has ever shown, there are no hidden internal components. This is the paradox at the heart of this story. Everything in your daily experience, every physical intuition you have ever developed, tells you that mass requires size. Mass means material. Mass means substance filling a volume. Heavier things are bigger because they contain more stuff. But the electron flatly contradicts this. It has mass without having any detectable spatial extent. It weighs something without being made of anything smaller. It resists your push without having any volume of material doing the pushing. And the electron is not alone in this. Every fundamental particle in the standard model of particle physics appears point-like in the same way. Quarks, despite being the components of protons and neutrons, have no detectable internal structure of their own. Neutrinos, the ghostly particles that pass through ordinary matter almost without interacting, are point-like. Muons and tau particles, heavier cousins of the electron, are point-like. Even the particles that carry forces, photons and gluons, and the W and Z bosons, do not have measurable spatial extent in the way that composite objects like protons and atoms do. The standard model treats all of these fundamental particles as having no internal structure and no built-in radius. But I want to be very precise about what point-like actually means, because it is easy to overstate the claim. When physicists say the electron is point-like, they are making an experimental statement, not a philosophical one. They are saying that every experiment conducted so far, at every energy scale we have probed, has found no evidence of internal structure or finite size. The electron behaves exactly as a point particle would at every scale we have tested. But physicists are not claiming, as a matter of absolute certainty, that the electron is a literal mathematical point occupying zero volume in some final metaphysical sense. That would be a much stronger claim than the experimental evidence supports. What the experiments actually establish is an upper limit on the electron's possible size. They tell us the electron is no larger than about 10 to the negative 18 meters. That is a ceiling, not a measurement. The electron could still have some incredibly tiny physical extent, perhaps at scales far smaller than our accelerators can reach. Some theoretical frameworks propose exactly this. But whatever its ultimate nature, the experimental fact remains. The electron carries real mass while exhibiting no detectable size. The old assumption, the one that says mass requires volume, mass requires material, mass requires physical bulk, simply does not hold at this level of reality. Something fundamentally different is going on. Mass, for a fundamental particle, is not about how much tiny material fills a tiny space. It is not about substance. It is not about volume. It is about something deeper, something that has nothing to do with physical size at all. And understanding what that deeper something is requires us to rethink what mass actually means from the very foundations. You learned as a child that heavier things are bigger. You carried that intuition through your entire life. It served you brilliantly in the everyday world of rocks and trucks and bowling balls. But the electron is nature's way of telling you that your intuition, however useful, was never the whole story. At the deepest level of reality, mass and size are entirely separate properties. They are independent. They can exist apart from each other. And in the case of every fundamental particle we have ever studied, they do. So the electron has mass, but no detectable size. Something is clearly wrong with our intuition. And the problem is not with the electron. The problem is with how you have been thinking about mass your entire life. You have been carrying around a definition of mass that works perfectly well in the everyday world, but quietly falls apart at the deepest level of reality. And to see why, we need to go back to the very beginning and ask a question that sounds almost embarrassingly simple. What is mass? If you asked most people this question, they would give some version of the same answer. Mass is how much stuff something contains. Mass is the amount of material in an object. Mass is how heavy something is. The more matter you pack into a volume, the more mass it has. These answers feel correct because they match everyday experience. A brick has more mass than a feather because there is more densely packed material in the brick. A full suitcase has more mass than an empty one because you added stuff to it. A planet has more mass than a pebble because the planet contains incomprehensibly more atoms. In all these cases, mass tracks directly with the amount of physical substance present. More material, more mass. Less material, less mass. No material, no mass. It seems utterly obvious. But obvious is not the same thing as correct. And this definition, mass equals amount of stuff, is not actually how physics defines mass at all. It never has been. This folk definition is a useful approximation that works for everyday objects, but it is not the real definition. The real definition is something quite different, and it has been sitting in plain sight for over 300 years. Isaac Newton published his masterwork, the Principia, in in 1687. In it, he laid down the laws of motion that would govern physics for the next 2 centuries. And right there, in the foundations of classical mechanics, Newton gave a definition of mass that has nothing whatsoever to do with volume or material content. Newton defined mass as resistance to acceleration. That is it. Mass in Newtonian physics is how hard it is to change an object's state of motion. Push on something and measure how much it resists your push. That resistance is its mass. Newton expressed this in what we now call his second law of motion. Force equals mass times acceleration. If you apply a known force to an object and measure how quickly it accelerates, you can calculate its mass. If the object barely budges, it has a lot of mass. If it shoots forward easily, it has very little mass. Mass, defined this way, is about behavior. It is about how an object responds when you try to move it. It says absolutely nothing about what the object is made of, how big it is, or whether it has any internal structure at all. Think about what that means. Newton's definition does not mention size. It does not mention volume. It does not mention the number of atoms or the density of material. It mentions only one thing: resistance to being pushed. If something resists acceleration, it has mass. Period. The definition is completely silent on every other property. An object could be large or small, solid or hollow, made of atoms or made of something utterly alien. None of that matters. All that matters is how it responds to force. If it resists acceleration, it has mass. This distinction between the folk definition and the physics definition is subtle but crucial. In everyday life, both definitions give the same answers. A brick has more mass than a feather by both definitions. It contains more material, and it also resists acceleration more. A bowling ball has more mass than a tennis ball by both definitions. More stuff inside, more resistance to pushing. So the two definitions appear identical, and most people never notice the difference. But they are not identical. They are logically distinct claims about what mass actually is, and they diverge dramatically when you get to fundamental particles. Galileo Galilei understood this property of mass before Newton formalized it, though he did not use the same language. Galileo realized through careful experiments, rolling balls down inclined planes, dropping objects of different weights, studying pendulums, that the tendency of an object to resist changes in its motion is a fundamental property of matter. He called it inertia. A ball sitting still on a flat surface will remain still unless something pushes it. A ball rolling on a flat surface will keep rolling unless something stops it. This was revolutionary in Galileo's time because Aristotle had taught that objects naturally come to rest. You push something, it moves, and then it stops. Galileo showed that stopping is not natural. Stopping requires a force, like friction or air resistance. Without those forces, the object would keep moving forever. Inertia, this tendency to keep doing what you are already doing, is the core of what mass means in physics. Mass is not how much stuff you have. Mass is how much inertia you have. It is how stubbornly you resist having your motion changed. And there is nothing in this definition that requires the massive object to be made of smaller pieces, to have a finite volume, or to contain any internal structure at all. Inertia is a behavioral property. It describes what an object does, not what an object is made of. Here is an analogy that might help. Think about electrical charge. An electron has a negative electric charge. That charge is a real, measurable, physically consequential property. It determines how the electron interacts with electric and magnetic fields. It governs chemical bonding, electrical conductivity, the behavior of circuits, and the structure of atoms. But nobody asks what the charge is made of. Nobody wonders how much physical space the charge occupies inside the electron. Nobody imagines tiny granules of charge packed into a little container. Charge is simply a property that the electron has. It is intrinsic. It is not constructed from smaller charge-carrying components. It is just a feature of being an electron. Mass works the same way, but our everyday experience makes it much harder to see. Because heavy objects in daily life are always big objects made of many parts, we unconsciously assume mass must be a summation of material. We think mass is built up from pieces, accumulated from parts, stored inside a volume. But at the fundamental level, mass is just a property, like charge. A particle has a certain amount of mass. That mass is intrinsic. It is not assembled from smaller mass-carrying components inside the particle. It is simply a feature of the particle's existence. Now, Newton's definition of mass was deep, but it was not the final word. In 1905, a young physicist named Albert Einstein published a paper that would transform the concept of mass forever. Einstein's special theory of relativity introduced the most famous equation in all of science. E equals mc squared. Energy equals mass times the speed of light squared. This equation says something staggering. Mass and energy are not just related, they are the same thing. They are two faces of one underlying reality. Mass is a form of energy. Energy is a form of mass. They are interconvertible. You can turn mass into energy and energy into mass. The speed of light squared is just the conversion factor, an enormous number that tells you how much energy is locked inside a given amount of mass. Before Einstein, physicists treated mass and energy as completely separate concepts. Mass was stuff. Energy was the ability to do work, to move things, to heat things, to light things. They were measured in different units. They obeyed different conservation laws. They seemed to have nothing in common. Einstein showed that this separation was an illusion. Mass is energy. Specifically, mass is concentrated, stored energy. When you hold a rock in your hand, the mass you feel is not the weight of stuff. It is the weight of energy. The rock's mass is energy bound up in the quarks and gluons and electromagnetic fields inside its atoms, energy that manifests as resistance to acceleration, as gravitational attraction, as weight on a scale. This changes everything about how you should think about mass. In the old picture, mass was fundamentally about material, tiny solid pieces with inherent heaviness packed into a volume. In Einstein's picture, mass is fundamentally about energy, and energy does not need to occupy a specific volume. Energy does not need to be made of tiny solid pieces. Energy is a property of fields and interactions and configurations. It can exist in forms that have nothing to do with physical size. Think about a compressed spring. When you compress a spring and hold it in place, you add energy to it. You do work against the spring's resistance, and that energy gets stored as elastic potential energy. Einstein's equation tells you that this stored energy has mass. The compressed spring is ever so slightly heavier than the relaxed spring. Not because you added any material. The spring contains exactly the same atoms before and after compression. You did not add a single particle, but you added energy, and energy is mass. The compressed spring has more inertia. It resists acceleration more. It weighs more on a sufficiently precise scale. The amount of extra mass is absurdly tiny, far too small to measure with any practical scale, but it is real. It is not metaphorical. It is a physical consequence of the equivalence of mass and energy. You added energy without adding material, and the mass increased. This demonstrates, in a simple everyday example, that mass is not about material content. Mass is about energy content. Or consider a box of light. Imagine a perfectly reflective box, a container whose inner walls are perfect mirrors. Now fill it with photons, with light bouncing back and forth inside. Photons have no rest mass. A single photon, by itself, has zero mass. But the photons carry energy, and they carry momentum. The total energy of all the photons bouncing around inside the box contributes to the box's mass. The box with light inside is heavier than the empty box. If you tried to push the filled box, it would resist acceleration more than the empty box, because the energy of the trapped light gives the system additional inertia. You added mass without adding any massive particles. The light itself, which has zero rest mass, contributes real, measurable mass to the system. Mass came from pure energy, with no material substance involved at all. This is not a thought experiment from science fiction. It is a straightforward consequence of special relativity, confirmed by decades of precision experiments. Mass is energy, and energy does not require physical volume. Energy does not require internal structure. Energy does not require tiny, solid pieces packed together. Energy can be stored in the vibration of a field, in the motion of a particle, in the tension of a force, in the curvature of space-time. None of these forms of energy have a size in the way that a brick or a bowling ball has a size. And yet, all of them contribute to mass. There is another example that makes this even more vivid. When an electron meets its antimatter counterpart, a positron, the two particles annihilate each other completely. The electron and positron vanish. Every last trace of them disappears. And in their place, pure energy emerges, typically in the form of two gamma-ray photons flying off in opposite directions. The mass of the electron and the mass of the positron have been entirely converted into massless light. The stuff is gone. The material has vanished. But the energy remains, carried away by the photons. Nothing was destroyed. The energy that once manifested as the mass of two particles now manifests as the energy of two photons. Mass became light. And the reverse happens too. When a sufficiently energetic gamma ray passes close to an atomic nucleus, the photon can vanish, and in its place an electron and a positron appear, two massive particles conjured from a single beam of massless light. This is called pair production, and it has been observed in laboratories countless times. It is not exotic or speculative. It is routine physics. Mass can be created from pure energy. Energy with no size, no volume, no material content can transform into particles with real, measurable mass. If mass can be created from massless light, if mass can be destroyed and turned back into massless light, then mass was never about material in the first place. It was always about energy. Material is just one particularly stable way of organizing energy. But energy itself does not need material to exist. It does not need volume. It does not need size. It simply needs to be there, and wherever it is, it carries inertia. Wherever it is, it has mass. Einstein's insight also introduced the concept of rest mass, sometimes called invariant mass. This is the mass a particle has when it is sitting still, not moving relative to you. For everyday objects, rest mass is just normal mass. The mass of a rock sitting on a table is its rest mass. But in relativity, the distinction matters because a moving particle behaves as though it has more inertia than a stationary one. The faster a particle moves, the harder it becomes to accelerate it further. At speeds approaching the speed of light, the resistance to acceleration grows without bound. This is why nothing with mass can ever reach the speed of light. You would need infinite energy to accelerate it that last tiny fraction. Rest mass is the intrinsic mass. It is the mass that belongs to the particle itself, independent of its motion. And here is the key point. Rest mass is a Lorentz invariant quantity. This means every observer, regardless of how they are moving, agrees on the value of a particle's rest mass. You could be standing still, flying in a rocket at half the speed of light, or orbiting a black hole, and you would all measure the same rest mass for an electron. It is a fundamental, observer-independent property. And crucially, rest mass is a property that does not logically require spatial extent. There is nothing in the mathematical framework of special relativity that connects a particle's rest mass to its physical size. Rest mass is a scalar quantity, a single number associated with the particle. It tells you how the particle responds to forces. It tells you how much energy is bound up in the particle's existence. But it does not tell you how big the particle is, because mass and size are independent properties. Relativity makes this explicit. Mass is defined through its dynamical role, through how it appears in the equations of motion, through its relationship to energy and momentum. It is not defined through geometry or volume. Let me draw out another consequence that might help. In Newtonian gravity, mass does two things. It resists acceleration, which is inertial mass, and it generates and responds to gravitational fields, which is gravitational mass. These seem like completely different roles. One is about pushing and shoving, the other is about gravitational attraction. But experiments have shown with extraordinary precision that inertial mass and gravitational mass are always exactly equal. Laurent-Ottevauche performed some of the earliest precision tests in the late 1800s and early 1900s, using a delicate torsion balance to compare how different materials responded to gravity versus how they resisted acceleration. His results, and every experiment since, confirmed that the two types of mass are identical to within at least 1 part in a trillion. Einstein took this equality and made it the foundation of general relativity. He called it the equivalence principle. The fact that inertial mass and gravitational mass are identical is not a coincidence. It reflects something deep about the nature of space-time. Gravity is not a force pulling massive objects together. Gravity is the curvature of space-time caused by the presence of energy and mass. Objects follow the straightest possible paths through curved space-time, paths called geodesics, and those paths look like gravitational attraction from our perspective. But notice what the equivalence principle does not say. It does not say that gravitational attraction requires size. It does not say that inertia requires volume. It says that whatever property causes a particle to resist acceleration is the same property that causes it to curve space-time and respond to gravity. That property is mass. And mass, as Einstein showed, is energy. A particle can resist acceleration, curve space-time around itself, and respond to gravitational fields without having any detectable physical radius, because all of these behaviors are consequences of having energy, not consequences of having size. This is worth pausing on, because it answers one of the most natural objections people raise when they first hear that fundamental particles might have no size. They ask, how can something with no size bend spacetime? How can something with no volume create a gravitational field? It seems as though you need to be somewhere, to occupy a location with spatial extent, to exert gravitational influence. But general relativity says otherwise. General relativity says that space-time curvature responds to energy and momentum, not to volume. A point with energy curves space-time. A point without energy does not. The curvature depends on how much energy is present, not on how much space the energy fills. You could concentrate the entire mass of the Earth into a point, and it would still curve space-time by exactly the same amount at every distance outside the original surface. The gravitational field of a point-like object is perfectly well defined at every point in space outside the object itself. There is no requirement that the source of gravity have any particular size or shape or internal structure. This is a profound shift. In the everyday world, you push a heavy box and it resists because there is a lot of dense material in the way. The material has inertia. More material, more inertia, more resistance. The connection between material and resistance seems causal. The material is what does the resisting. But physics tells a different story. The resistance does not come from the material itself. The resistance comes from the energy associated with the system. The material is just one way that energy can be organized. Remove the material entirely, keep only the energy, and the resistance remains. Consider the proton for a moment. A proton is not a fundamental particle. It is made of quarks and gluons. It has internal structure and a measurable size, roughly 1 femtometer across, which is about 10 to the negative 15 meters. But here is a remarkable fact that we will explore in much greater detail later. The quarks inside the proton get their individual rest masses from interactions with the Higgs field. If you add up the rest masses of the 2 up quarks and 1 down quark inside a proton, you get roughly 1% of the proton's total mass. Just 1%. The other 99% comes from the kinetic energy of the quarks zooming around inside the proton, and from the energy stored in the gluon fields binding the quarks together. 99% of the mass of every proton in your body is not material. It is energy. Pure energy, stored in the motion of quarks and the tension of gluon fields. This is Einstein's equation made tangible. The mass of your body, the weight you feel when you stand on a scale, is overwhelmingly energy, not stuff. And if 99% of a proton's mass is energy rather than the intrinsic mass of its parts, then the idea that mass fundamentally requires material content is already broken, even before we get to fundamental particles. The proton already shows us that mass can come from energy stored in fields and motion, rather than from physical substance packed into a volume. Now extend this thinking to the electron. The electron is not composite. It has no known parts. But it has rest mass. Where does that rest mass come from, if not from internal components? The answer, which we will explore shortly, involves quantum fields and their interactions. But the conceptual groundwork is already in place. Mass is not material. Mass is energy. Mass is a dynamical property, a measure of how a particle interacts with forces and fields. It describes behavior, not substance. It tells you what a particle does when you push it, not what tiny material fills its interior. There is one more important point to make before we move on. The idea that mass is something a particle does, rather than something a particle is made of, might sound strange, even unsettling. We are so accustomed to thinking of mass as a tangible, concrete, material thing that redefining it as a behavioral property feels like taking something real and replacing it with an abstraction. But the behavioral definition is not less real. It is more real. It captures what mass actually does in the equations of physics. It describes the actual role that mass plays in determining how things move, how things interact, and how the universe evolves. The folk definition, mass as amount of stuff, is the abstraction. It is a mental shortcut that works for everyday objects, but has no foundation in fundamental physics. Think about it this way. When you say a rock has mass, what you really mean is that the rock exhibits certain behaviors. It resists acceleration. It falls when you drop it. It curves space-time around itself by a tiny amount. It responds to gravitational fields from other objects. These are the things mass does. These are the observable, measurable consequences of having mass. And none of them require the massive object to have a specific size or a specific internal composition. A point particle with mass would resist acceleration exactly as stubbornly as a tiny sphere with the same mass. It would fall in a gravitational field in exactly the same way. It would curve space-time by exactly the same amount. Every single physical consequence of having mass would be identical, regardless of whether the massive object was a sphere, a cube, a cloud, or a structureless point. The effects of mass do not depend on size or shape. They depend only on the amount of mass itself. This is why the electron's situation, mass without detectable size, is not a contradiction. It is not a paradox in the logical sense. It only seems paradoxical because our everyday intuition conflates two properties that are actually independent. We grew up in a world where massive things always happen to be big, and we mistakenly concluded that mass requires bigness. But physics never made that claim. Physics defined mass as inertia, as resistance to acceleration, as energy content. Physics was always compatible with the possibility of mass without size. It took experiments at the subatomic scale to reveal that this possibility is not just theoretical. It is how reality actually works. So where does the electron's rest mass come from? If not from internal material, if not from smaller parts packed into a volume, if not from the accumulated weight of hidden components, then what gives the electron its mass? What mechanism, what interaction, what physical process endows a structureless, point-like particle with a specific, precise, measurable amount of rest mass? The answer lies not inside the electron, but outside it. It lies in the fields that fill all of space, fields that every particle interacts with at every moment of its existence. The electron's mass is not stored within the electron. It is generated by the electron's relationship with something much larger and more fundamental. And understanding that relationship requires us to leave behind the world of classical physics entirely and enter the quantum realm, where particles are not tiny objects sitting in empty space, but ripples in fields that permeate the entire universe. To understand where the electron's mass actually comes from, you need to abandon one of the most deeply rooted pictures in your mind. You need to stop thinking of particles as tiny objects sitting in empty space. Because that picture, as intuitive as it feels, is wrong. The universe is not made of little balls bouncing around in a void. The universe is made of fields. And everything you have ever seen, touched, or measured, every particle, every force, every interaction, is a consequence of those fields behaving in certain ways. A field, in physics, is something that has a value at every point in space and at every moment in time. You are already familiar with fields in everyday life, even if you do not call them that. Temperature is a field. At every point in a room, there is a temperature. Near the heater, the temperature is higher. Near the window in winter, it is lower. The temperature varies smoothly from point to point, forming a temperature field that fills the entire room. You cannot pick up a chunk of temperature and hold it in your hand. Temperature is not a thing. It is a property that exists everywhere in the room simultaneously. You can measure it at any point, but it does not have a size or a shape. It is spread throughout space. Gravity is another example. The gravitational field of the Earth exists at every point in space around the planet. Close to the surface, the field is strong. Far away, it weakens. At every point, the field has a strength and a direction, pointing toward the center of the Earth. You move through this field right now as you sit or stand. It pulls on you constantly, but you cannot see it. You cannot pick it up. It has no material substance. It is simply there, a property of space itself created by the Earth's mass. Michael Faraday, working in the 1830s and 40s, introduced the concept of fields to describe electricity and magnetism. Before Faraday, physicists imagined electric and magnetic forces as mysterious actions at a distance. One charged object somehow reached across empty space and pushed or pulled on another charged object. This troubled Faraday deeply. How could something act where it is not? His answer was the field. A charged object does not reach across space. Instead, it creates a field that fills the surrounding space, and that field acts on other charged objects wherever they happen to be. The force is not action at a distance. The force is local. The field is right there, at the location of the second charge, and the second charge responds to the field at its own location. James Clerk Maxwell formalized Faraday's intuition into precise mathematical equations in the 1860s. Maxwell's equations describe how electric and magnetic fields are created, how they change over time, how they interact with charged particles, and how they propagate through space as electromagnetic waves. Light, Maxwell showed, is an electromagnetic field rippling through space. Radio waves, microwaves, X-rays, gamma rays, all are the same field oscillating at different frequencies. The electromagnetic field is not a mathematical abstraction. It is a real, physical entity that carries energy and momentum. It can push things. It can heat things. It can carry information across billions of miles. It is as real as any rock or brick, even though it has no material substance in the traditional sense. Now here is where things become truly extraordinary. In the 20th century, physicists discovered that every fundamental particle in the universe is associated with its own quantum field. The electron is not a tiny ball. The electron is an excitation, a ripple in the electron field, a quantum field that fills the entire universe. Everywhere in space, right now, the electron field exists. In most places, the field is in its ground state, its lowest energy configuration. Nothing is happening, no electron is present. But when the field gets excited, when energy gets added to it in the right way, a ripple forms. That ripple is what we observe and measure as an electron. Think of a pond on a windless day. The surface is smooth and flat. The water is there, filling the pond, but nothing interesting is happening at the surface. Now drop a pebble in. A ripple forms. The ripple has a definite location. It moves. It carries energy. It interacts with other ripples. From a distance, you might describe the ripple as a thing, an object moving across the water. But it is not a separate thing. It is a disturbance in the water. The water was already there. The ripple is just the water doing something. Particles work the same way. The electron field is the pond. An electron is a ripple in that pond. The ripple carries energy, momentum, charge, and mass. It behaves like a particle in experiments. It scatters off other particles. It orbits nuclei. It flows through wires as electric current. But fundamentally, it is not a separate object sitting in space. It is a localized excitation of a field that permeates everything. This is a genuinely radical idea, and it deserves more than a passing mention, because it changes the meaning of the word particle in a fundamental way. When you hear the word particle, you picture a tiny thing, a speck, a grain, a miniature object with a definite boundary, sitting at a definite location in otherwise empty space. The space is one thing. The particle is another. They are separate. The particle is in the space, the way a marble is in a jar. But quantum field theory says this picture is completely wrong. There is no separate particle sitting in empty space. There is only the field. The field is already there. everywhere, filling all of space. What you call a particle is the field doing something specific, vibrating in a particular way, carrying a specific quantum of energy. The electron is not in the electron field. The electron is the electron field, momentarily excited at a particular location. Remove the excitation and the electron is gone, but the field remains. The field is primary. The particle is secondary. The particle is what happens when the field vibrates. This means that empty space is not truly empty. Even when no particles are present, every quantum field still exists in its ground state, its lowest energy configuration, humming quietly in the background. The electron field is there. The quark fields are there. The photon field is there. All of them, filling every cubic centimeter of the universe, even in the deepest vacuum of intergalactic space. When physicists say the vacuum is not empty, this is what they mean. The fields are always present. Particles are just what we see when those fields get excited. And this is why asking about the physical size of a fundamental particle is a fundamentally different kind of question than asking about the size of a marble or a grain of sand. A marble is a separate object with a clear boundary. An electron is a ripple in a field. Asking for the spatial extent of a ripple is not the same as asking for the dimensions of an object. A ripple does not have a hard edge. It does not have an inside and an outside in the way a marble does. It is a pattern of activity in a medium. Its properties, including its mass, come from the rules governing the field, not from the geometry of a tiny container. This is quantum field theory, and it is the most successful framework in the history of science. Every particle has its own field. The electron has the electron field. Quarks have quark fields, one for each type. Photons are excitations of the electromagnetic field. Gluons are excitations of the strong force field. Neutrinos have neutrino fields. Every fundamental particle in the Standard Model is a ripple in a corresponding quantum field that fills all of space. This picture completely transforms the question of mass. In the old particle as tiny ball picture, you asked where the mass was located. Was it inside the ball? Was it packed into its volume? But in the field picture, that question dissolves. The particle is not a ball with an inside. The particle is a pattern of excitation in a field. Asking where its mass is located is like asking where the speed of a wave is located. Speed is not stored in a particular spot inside the wave. Speed is a property of the wave's behavior, of how the pattern moves through the medium. Mass, similarly, is a property of how the field excitation behaves. It is not stored in a tiny volume. It arises from the nature of the field itself, and from how that field interacts with other fields. And this brings us to the Higgs field. In the 1960s, several physicists independently proposed a mechanism that could explain how fundamental particles acquire rest mass. The key papers were published in 1964 by three groups working separately. Peter Higgs published his work, François Englert and Robert Brout published theirs, and Gerald Guralnick, C.R. Hagen, and Tom Kibble published a third paper exploring the same mechanism. Although the discovery is often associated with Higgs's name alone, all three groups contributed essential pieces. The mechanism they described involves a new quantum field, one that had not been observed before, and whose existence was purely a theoretical proposal at the time. This field, now called the Higgs field, is unlike the other fields in the Standard Model in one crucial respect. In empty space, at the lowest energy state, the Higgs field is not zero. Every other field in the Standard Model settles to zero in its ground state. When nothing is happening, the electromagnetic field is zero. The electron field is zero. The quark fields are zero. But the Higgs field does not settle to zero. Its lowest energy state, its vacuum state, has a non-zero value everywhere in space. This seems like a technical detail, but it changes everything. Because every particle that interacts with the Higgs field is always, at every moment, in contact with a field that has a non-zero value. And that constant interaction is what gives particles their rest mass. Here is one way to think about it. Imagine you are walking through an empty room. Nothing is in your way. You can stride freely at whatever pace you choose. You have no resistance to your motion. Now imagine the room is filled with a thick, invisible substance, something like molasses or honey permeating every inch of space. As you try to walk through it, you feel resistance. Every step requires effort. You push forward, and the molasses pushes back. Your motion is sluggish. It takes more force to accelerate. You have, effectively, gained inertia. Not because anything was added to you, not because your body changed in any way, but because you are interacting with something that fills the space around you. The Higgs field works somewhat like this. A particle moving through space is constantly interacting with the non-zero Higgs field. That interaction creates resistance to acceleration. The particle behaves as though it has inertia. It behaves as though it has mass. And the amount of mass depends on how strongly the particle couples to the Higgs field. Particles that interact with the Higgs field very strongly acquire a lot of mass. Particles that interact weakly acquire only a little. And particles that do not interact with the Higgs field at all, like the photon, remain massless.
I should be careful with this analogy because it is imperfect in important ways. The Higgs field does not literally slow particles down the way molasses slows a person. A massive particle can still move at any speed below the speed of light. It does not gradually decelerate the way you would in actual molasses. What the Higgs interaction does is more subtle. It gives the particle a property, rest mass, that makes it harder to change the particle's state of motion. A particle with mass requires force to accelerate. A particle without mass does not. The Higgs field does not drag on the particle. It changes what kind of particle it is, from a massless one that must always travel at the speed of light, to a massive one that can sit still, that can be sped up or slowed down, that resists being pushed. Think of it more precisely this way. Without the Higgs field, the equations governing fundamental particles would have a particular symmetry. In a universe with this symmetry intact, all the fundamental particles would be massless. They would all travel at the speed of light, just like photons do now. None of them could ever be at rest. None of them could form atoms or build structures. The universe would be a blaze of massless particles streaming through space at light speed, never clumping, never combining, never forming anything interesting at all. The Higgs field breaks this symmetry. When the Higgs field settles into its non-zero ground state, the symmetry is spontaneously broken, and this breaking is what gives certain particles mass. The particles that couple to the Higgs field acquire rest mass through that coupling. They slow down from light speed. They become capable of sitting still. They gain the ability to resist acceleration. They become, in a word, massive. The symmetry breaking is spontaneous because nothing forces it from outside. The Higgs field settles into a non-zero state on its own because that state has the lowest energy. It is like a ball rolling to the bottom of a valley. Nobody pushes the ball. It just rolls downhill because downhill is where the lowest energy is. But imagine a very specific kind of valley. Picture a landscape shaped like the bottom of a wine bottle or like a sombrero, a hat with a brim. In the center, there is a bump, a local hilltop. And all around that hilltop, at equal distances in every direction, there is a circular trough, a ring-shaped valley. The hilltop is symmetrical. If you stood at the very peak, every direction would look the same. There is no preferred direction. The symmetry is perfect. Now place a ball at the top. The ball sits on the peak of perfect symmetry, but the peak is unstable. Any tiny nudge,
any infinitesimal disturbance, and the ball rolls down into the trough. It has to land somewhere in the trough, and wherever it lands, it picks a direction. The symmetry is broken. Not by anything external pushing the ball in a particular direction, but by the ball simply finding a lower energy state. The ball had to fall. It had no choice. But where it fell was arbitrary. The symmetry was spontaneously broken by the system finding its lowest energy configuration. The Higgs field does something analogous, but in the abstract space of field values. At very high energies, like those that existed in the first moments after the Big Bang, the Higgs field sat at the symmetric peak, at a value of 0. But as the universe cooled, that peak became unstable. The Higgs field rolled down to a non-zero value, like the ball rolling into the trough. It settled into a particular state. That state is what we call the vacuum, the emptiest possible configuration of the universe. But it is not truly empty, because the Higgs field has a non-zero value everywhere. The vacuum itself is permeated by the Higgs field. The amount of rest mass a particle gets depends on a number called the coupling constant. Each particle type has its own coupling constant to the Higgs field. The electron has a relatively small coupling constant, so it gets a small rest mass. The top quark, the heaviest fundamental particle we know of, has an enormous coupling constant, so it gets a rest mass roughly 340,000 times larger than the electron. The photon has a coupling constant of 0, so it gets no mass at all. It remains completely massless, travelling at the speed of light, unaffected by the Higgs field. Why different particles have different coupling constants is a deep and currently unanswered question. The Standard Model does not explain these values. It takes them as inputs, numbers that must be measured experimentally and plugged into the theory. The theory tells you that if the electron's coupling constant to the Higgs field has a certain value, then the electron will have a certain mass. But it does not tell you why the coupling constant has that particular value rather than some other value. This is one of the open problems in fundamental physics. Something deeper, some theory beyond the Standard Model, presumably determines these coupling constants, but we do not yet know what that theory is. Now, the crucial insight for our story. Notice what has happened. The electron has mass not because something is packed inside it, not because there are smaller particles within it whose individual masses add up, not because there is a tiny volume of dense material doing the resisting. The electron has mass because of its interaction with a field that fills all of space. The mass is relational. It comes from the coupling between the electron field and the Higgs field. It is a property that arises from the relationship between two fields, not from the internal composition of a little object. This is why the electron can be point-like and still have mass. Mass does not require internal structure. Mass does not require spatial extent. Mass requires interaction with the Higgs field. And that interaction happens regardless of whether the particle has a measurable size or not. A point-like excitation in the electron field interacts with the Higgs field in exactly the same way that a tiny sphere would. The coupling constant does not depend on the particle's radius. It depends on the nature of the field and the mathematical structure of the interaction. The particle could have a size of a femtometer, a size of an attometer, or no detectable size at all. Its mass would be the same in every case, because the mass comes from the field interaction, not from the geometry. This is arguably the single most important idea in this entire story. Mass is not a geometric property. Mass is a field property. It is determined by how a particle's quantum field couples to the Higgs field. It has nothing to do with volume or shape or internal structure. The electron is point-like and massive for the same reason a ripple on a pond can carry energy without having a solid core. The ripple is a pattern in the field. Its properties come from the nature of the field and from the rules governing the pattern, not from any material packed into the ripple. For decades, the Higgs field was a theoretical proposal. an elegant mechanism that solved deep problems in particle physics but had not been directly confirmed by experiment. The theory predicted that if the Higgs field exists, it should be possible to excite it in the same way you can excite any quantum field, by adding enough energy. Just as adding energy to the electromagnetic field creates a photon, and adding energy to the electron field creates an electron, adding energy to the Higgs field should create a Higgs boson. The Higgs boson would be a new particle, a ripple in the Higgs field with specific predicted properties. Finding the Higgs boson became one of the most important goals in the history of experimental physics. But there was a problem. The theory did not predict the exact mass of the Higgs boson. It could have been in a wide range. And detecting it required enormous energies, because the Higgs boson, if it existed, was expected to be very heavy by particle physics standards. Building a machine capable of producing and detecting it required decades of engineering and billions of dollars in investment. That machine was the Large Hadron Collider at CERN, near Geneva, Switzerland. The LHC is the largest and most powerful particle accelerator ever built. It is a ring 27 kilometers in circumference, buried underground beneath the French-Swiss border. Inside the ring, two beams of protons are accelerated to within a tiny fraction of the speed of light, and then steered into head-on collisions. The energy of these collisions is so great that new particles are created from the collision energy, in accordance with Einstein's equation E equals mc squared. Among the shower of particles produced in each collision, physicists searched for the signature of the Higgs boson. The search took years. Thousands of physicists from dozens of countries worked on the project. Two independent detector teams, known as ATLAS and CMS, each built enormous instruments to capture and analyze the debris from proton collisions. The detectors themselves are marvels of engineering, as large as multi-story buildings, packed with millions of sensors designed to track the paths and measure the energies of particles flying out from each collision. Every second, the LHC produces hundreds of millions of collisions. The detectors record a tiny fraction of those, the ones most likely to contain something interesting. Computers sort through billions of events, searching for patterns consistent with the Higgs boson's predicted decay products. It is like listening to the static of a billion radios and trying to pick out a single specific melody. On July 4, 2012, the two teams jointly announced that they had found it. In a packed auditorium at CERN, with Peter Higgs himself sitting in the audience, physicists presented evidence for a new particle consistent with the Higgs boson. The particle had a mass of approximately 125 giga-electron volts, which is roughly 133 times the mass of a proton. The discovery was confirmed with a statistical significance of 5 sigma, meaning the probability that the observed signal was a random fluctuation rather than a real particle was less than 1 in 3.5 million. Higgs, then 83 years old, wiped tears from his eyes. He had proposed this field nearly half a century earlier, in 1964, and had waited his entire career for experimental confirmation. The discovery was one of the greatest achievements in the history of science. It confirmed the existence of the Higgs field, the invisible field that fills all of space and gives fundamental particles their rest mass. Peter Higgs and François Englert were awarded the Nobel Prize in Physics in 2013 for their theoretical prediction. But the discovery did not answer every question. It confirmed that the Higgs field exists. It confirmed that fundamental particles get their mass through interaction with this field. But it did not explain why the coupling constants are what they are. It did not explain why the electron is so much lighter than the top quark. It did not explain why the Higgs boson itself has the mass it does. These remain open problems. The Higgs mechanism tells us how particles get mass, but it does not tell us why they get the specific masses they have. Something deeper remains to be discovered. There is another important subtlety. The Higgs mechanism explains the rest masses of fundamental particles, particles like electrons, quarks, and the W and Z bosons. These are the particles that appear point-like in experiments, with no detected internal structure. For these particles, the Higgs interaction is the origin of their rest mass. Without the Higgs field, they would be massless. But the Higgs mechanism does not account for the mass of composite particles like protons and neutrons. As I mentioned earlier, the quarks inside a proton get only about 1% of the proton's total mass from the Higgs field. The rest comes from a completely different source, the energy of the strong nuclear force binding the quarks together. This is a crucial distinction, and we will explore it in detail shortly. For now, the key point is that the Higgs field explains the rest mass of fundamental particles specifically, the particles that have no internal structure and no detectable size. Let me emphasize what the Higgs mechanism is not, because misconceptions are common. The Higgs field is not a substance that particles wade through like a liquid. Particles do not slow down as they move through it. The Higgs field is not a drag force. It does not resist motion. What it does is far more fundamental. It changes the very nature of the particles that interact with it. It transforms them from massless entities that must travel at the speed of light into massive entities that can exist at rest, that can accelerate and decelerate, that can form bound states and build atoms. It gives them the property of inertia, the property of rest mass, not by adding material to them, but by coupling to their quantum fields and altering their behavior. This mechanism also explains something that might otherwise seem arbitrary. Why does the photon have no mass while the electron does? Before the Higgs mechanism was understood, this difference had no deeper explanation. It was simply a fact about the universe, written into the equations by hand. But the Higgs mechanism reveals the reason. The photon does not couple to the Higgs field, the electron does. Their different masses are not arbitrary features of the universe. They are consequences of different coupling constants, different relationships to the same underlying field. The question of why a particle has the mass it does becomes a question about the structure of its interactions, not about the density of its material. And the Higgs field is not the only source of mass in the universe. As we will explore next, the vast majority of the mass you experience in daily life, the mass of atoms, the mass of your body, the mass of the Earth, comes not from the Higgs mechanism, but from the energy of the strong nuclear force. The Higgs field gives fundamental particles their rest mass, but those rest masses are tiny compared to the masses of the composite particles and structures built from them. The universe's mass budget is dominated by a completely different mechanism, one that illustrates the principle of mass-energy equivalence in the most dramatic way imaginable. But the conceptual breakthrough is already complete. You now understand, at least in principle, how a particle can have mass without having size. The particle is a ripple in a quantum field. Its mass comes from the coupling between that quantum field and the Higgs field. The coupling does not require the ripple to have a physical radius. It does not require internal structure. It does not require a tiny container filled with heavy material. Mass is a field property generated by the interaction between fields. It is not a volume property generated by the accumulation of matter. And this is why the deepest building blocks of reality can carry real, measurable mass, while appearing, in every experiment we have ever conducted, to occupy no detectable space at all. You now understand how fundamental particles like the electron get their rest mass. They interact with the Higgs field, the invisible quantum field that fills all of space with a non-zero value, and that interaction gives them inertia, the property we call mass. The electron has mass not because something is packed inside it, but because of how its quantum field couples to the Higgs field. Mass is a field property, not a volume property.
That is why the electron can be point-like and still resist when you push it. But there is an enormous piece of the story still missing, and it is a piece that might shock you when you grasp its full implications. Because here is the truth. The Higgs mechanism, as important as it is, accounts for only a tiny fraction of the mass you encounter in everyday life. When you step on a scale, when you lift a heavy box, when you feel the weight of your own body pressing against the ground, almost none of that mass comes from the Higgs field. Almost all of it comes from somewhere else entirely. To understand this, we need to look at the proton. The proton is the positively charged particle inside every atomic nucleus. Along with neutrons, protons make up the cores of all atoms. The number of protons in a nucleus determines which element you are dealing with. 1 proton makes hydrogen, 6 protons make carbon, 26 make iron, 79 make gold. Every atom in your body, every atom in the Earth, every atom in every star is built around protons and neutrons packed together in a nucleus. And the proton is fundamentally different from the electron. The electron, as far as any experiment has ever shown, is a fundamental particle. It has no internal parts, no substructure, no smaller components. But the proton is composite. It is made of smaller things. Specifically, each proton contains 3 quarks, 2 up quarks and 1 down quark, bound together by gluons, the particles that carry the strong nuclear force. The proton has a measurable size, roughly 1 femtometer across, which is about 10 to the negative 15 meters. If you fire high-energy particles at a proton and study the scattering patterns, you can see the internal structure clearly. The quarks show up as hard, point-like objects rattling around inside the proton. The gluons show up as the force field binding them together. Now here is the remarkable fact. The up quark has a rest mass of roughly 2.2 mega-electron volts. The down quark has a rest mass of roughly 4.7 mega-electron volts. These rest masses come from the Higgs mechanism, from the quarks coupling to the Higgs field, exactly as we discussed for the electron. If you add up the rest masses of the 2 up quarks and 1 down quark inside a proton, you get roughly 9.1 mega-electron volts. But the proton's total mass is about 938 mega-electron volts. Hear those numbers again. The quarks contribute about 9 mega-electron volts. The proton's total mass is about 938 mega-electron volts. The rest masses of the quarks account for less than 1% of the proton's mass. Just 1%. The other 99% comes from somewhere else. Where? From energy. Pure energy. The energy of the strong nuclear force. To understand why the strong force generates so much energy inside the proton, you need to understand something about what makes this force so different from every other force you have encountered. The strong nuclear force, described by the theory called quantum chromodynamics, or QCD, is unlike any force in everyday experience. It is not just stronger than electromagnetism or gravity. It is a fundamentally different kind of force, and it behaves in ways that defy everyday intuition. Start with the charge. Electromagnetism has one type of charge, electric charge, which comes in 2 varieties, positive and negative. Opposite charges attract, like charges repel, and that is essentially the whole story. The strong force is far more complex. Instead of 1 type of charge, it has 3, and physicists call them color charges. Not because quarks are literally colored, but because the mathematics of 3 charges mixing together reminded physicists of how 3 primary colors combine to make white. The 3 color charges are labeled red, green, and blue, and each one also has an anti-color counterpart: anti-red, anti-green, and anti-blue. Every quark carries one of these 3 color charges. A proton contains 3 quarks, 1 red, 1 green, and 1 blue, and together they combine to make a colorless or color-neutral composite particle.
But here is where things get truly strange. The force carrier of electromagnetism is the photon. Photons carry electromagnetic force between charged particles. But photons themselves have no electric charge. They are neutral. A photon does not interact with other photons through the electromagnetic force. It just carries the force between charged objects and otherwise minds its own business. Gluons are completely different. Gluons carry the strong force between quarks. But unlike photons, gluons themselves carry color charge. A gluon is not neutral. It carries one color and one anticolor simultaneously. This means gluons interact with other gluons. They pull on each other. They bind to each other. They generate more gluons. The force carrier itself is charged under the force it carries. This is like imagining a postal worker who is also a package. Every time a postal worker delivers a letter, the postal worker itself becomes another letter that needs delivering. And that delivery requires another postal worker who also becomes a letter. The system generates more and more of itself. This self-interaction of gluons has enormous consequences. It is the reason the strong force behaves so differently from electromagnetism at different distances. In electromagnetism, the force between two charged particles gets weaker as you move them apart and stronger as you bring them together. Simple and predictable. But the strong force does the opposite at the scales that matter inside a proton. When two quarks are very close together, almost on top of each other, the strong force between them is actually quite weak. The quarks behave almost as though they are free particles, barely interacting. This property, discovered in 1973 by David Gross, Frank Wilczek, and H. David Politzer, is called asymptotic freedom. It was so unexpected and so important that all three physicists received the Nobel Prize for it. But as you try to pull two quarks apart, the force does not weaken like gravity or electromagnetism would. It stays constant or even grows stronger. The gluon field between the separating quarks does not spread out and fade. Instead, it concentrates into a narrow tube of intense energy, sometimes called a flux tube or a color string. The farther you pull the quarks apart, the more energy you pour into this tube. The tube acts like an incredibly stiff rubber band, pulling the quarks back together with a force that does not diminish with distance. And if you pull hard enough, if you inject enough energy to stretch that tube far enough, something spectacular happens. The tube does not simply snap and release the quarks. Instead, the energy stored in the tube becomes so great that it converts into mass. A new quark-antiquark pair materializes out of the energy of the tube, right there in the middle of the stretched field. Where there were two quarks being pulled apart, now there are four quarks, rearranged into two new composite particles. You tried to isolate a single quark, and the universe responded by creating new quarks to make sure no quark ever ends up alone. This is confinement. It is one of the most extraordinary properties of the strong force. You can never, under any circumstances, isolate a single quark. Every quark must always be part of a color-neutral composite, either a group of three quarks forming a baryon, like a proton or neutron, or a quark-antiquark pair forming a meson, like a pion or kaon. The strong force literally will not allow quarks to exist independently. The energy required to separate them creates new quarks before separation can occur. No experiment has ever produced an isolated quark, and the theory of QCD explains exactly why it is impossible. Now think about what this means for the energy inside a proton. The three quarks are confined within a volume roughly 1 femtometer across. They are zooming around at speeds close to the speed of light, bouncing off the walls of their gluon prison. The gluon fields between them are fantastically intense. Gluons are constantly being created and absorbed, splitting into pairs, recombining, interacting with each other in a roiling storm of activity. The inside of a proton is not a quiet place with three tiny marbles sitting peacefully. It is an inferno of quantum field activity, a maelstrom of quarks and gluons interacting at unimaginable rates, generating enormous amounts of field energy in a space smaller than an atom's nucleus. All of that energy has mass. This is Einstein's equation at work. E equals mc squared. Energy equals mass times the speed of light squared. Energy is mass. Mass is energy. They are interconvertible. The enormous energy of the strong force confined within the proton manifests as the proton's mass. Let me put this in the starkest terms. When you stand on a bathroom scale and read your weight, roughly 99% of that number comes not from the Higgs mechanism, not from the rest masses of fundamental particles, but from the energy of gluon fields and quark motion inside the protons and neutrons in your atoms. You are overwhelmingly made of energy. Not in a vague metaphorical sense, in a precise, literal, physically measurable sense. The mass of your body is almost entirely the energy of the strong nuclear force, trapped inside the protons and neutrons of your atoms, manifesting as inertia, as weight, as the resistance you feel when you try to accelerate. This is one of the most extraordinary facts in all of physics. The mass of ordinary matter, the mass of everything you see and touch, the mass of planets and stars and galaxies, is not primarily stuff. It is primarily energy. The old intuition that mass means material content, that heavier things contain more substance, is not just slightly wrong. It is almost completely wrong. For protons and neutrons, 99% of their mass is energy, not substance. The tiny rest masses of the quarks inside are almost negligible. The overwhelming bulk of the mass comes from the roaring storm of gluons and quark motion confined within each proton and neutron. This has been confirmed through decades of theoretical work and computational verification. Calculating the proton's mass from first principles is extraordinarily difficult because the strong force is, well, strong. Unlike electromagnetism, where forces are weak enough that you can use approximation methods to get precise answers, the strong force at the distances inside a proton is so intense that standard approximation techniques fail. The mathematical tools that work beautifully for quantum electrodynamics, the theory of photons and electrons, produce nonsensical results when applied to the strong force at low energies. The coupling is too powerful. Perturbation theory, the physicist's favorite calculation method, breaks down completely. Physicists had to develop a completely different computational approach called lattice QCD. In this method, spacetime is discretized into a grid, a lattice of points, and the equations of quantum chromodynamics are solved numerically on powerful supercomputers. The quarks and gluons are placed on the lattice. The strong force interactions are computed step by step, and the properties of the proton emerge from the calculation. It is a brute force approach, replacing elegant pen and paper mathematics with sheer computational power. But it works. These computations take enormous amounts of computing power. Modern lattice QCD calculations run on some of the most powerful supercomputers in the world for months at a time, but the results are stunning. When you put in the quark masses from the Higgs mechanism and let the strong force do its work, out comes the proton mass. The calculated value matches the experimentally measured proton mass to within a few percent, and the precision improves every year as computers grow more powerful and algorithms improve. The 99% of the proton's mass that comes from strong force energy is not a guess or an estimate. It is a quantitative prediction of QCD, confirmed by direct computation. And here is the key connection back to our central question. Even this composite mass, the mass of the proton, does not require the fundamental constituents to have measurable size. The quarks inside the proton are themselves point-like, as far as any experiment can determine. The gluons are point-like. These structureless, sizeless fundamental particles generate the proton's mass through their energy of motion and their field interactions, not through the amount of space they occupy. The proton has a size, yes, roughly 1 femtometer, but that size is the size of the region where the quarks and gluons are confined. It is the size of the bound state, not the size of the fundamental particles themselves. The mass does not come from the volume of the quarks, it comes from the energy of their confinement. This is mass-energy equivalence in its most dramatic and tangible form. You do not need material packed into a volume to have mass. You need energy. And energy can be stored in the motion of particles, in the tension of force fields, in the vibrations of quantum fields, in the coupling between a particle and the Higgs field. None of these forms of energy require physical volume. None of them require internal structure. None of them require tiny, solid objects to carry the weight. So let us now return to the central question of this story and answer it directly. How can a particle have mass without having size? The answer has 3 layers, and each one reinforces the same fundamental point. First, mass is not what you think it is. Mass is not amount of stuff. Mass is not material content. Mass is not physical bulk. Mass is resistance to acceleration. Mass is energy content. Mass is how a particle interacts with fields and forces. It is a behavioral and relational property, not a geometric or volumetric one. Nothing in the definition of mass requires the massive object to occupy space. Second, fundamental particle rest mass comes from the Higgs mechanism. The electron, the quarks, the muon, the tau, the W and Z bosons, all of these fundamental particles acquire rest mass through their coupling to the Higgs field. The Higgs field fills all of space with a non-zero value. Particles that couple to it gain inertia. The strength of the coupling determines the amount of mass. This mechanism operates on the quantum field of the particle, not on a physical volume. It does not care whether the particle has a radius of a femtometer, an attometer, or no detectable radius at all. The coupling is a property of the field interaction, not of the particle's geometry. Third, the overwhelming majority of everyday mass comes from strong force energy inside composite particles. Protons and neutrons get 99% of their mass from the kinetic energy of quarks and the field energy of gluons, not from the rest masses of their constituents. This mass is real. It creates inertia. It generates gravity. It curves space-time. But it is energy, not material. The quarks and gluons that generate it are themselves point-like, without detectable size. Mass from energy does not require spatial extent. Each of these layers tells the same story from a different angle. Mass and size are independent properties. They happen to correlate in everyday life because everyday objects are large collections of atoms, and more atoms means more mass and more volume simultaneously. But this correlation is not a law of nature. It is an accident of scale. At the fundamental level, the correlation breaks completely. Fundamental particles carry mass without carrying volume. They resist acceleration without having a measurable radius. They are heavy without being big. Now, I want to address something important about what we do and do not know. When I say the electron appears point-like, I am stating the current experimental situation. Every experiment conducted so far, at every energy we have probed, has found no evidence that the electron has internal structure or finite size. The upper limit on the electron's radius, set by the most precise scattering experiments, is roughly 10 to the negative 18 meters. Below that scale, we simply do not know. This means the statement that the electron is point-like is an experimental bound, not a final metaphysical verdict. It is entirely possible that the electron has some incredibly tiny internal structure at scales far below what our current accelerators can reach. Some theoretical frameworks propose exactly this. String theory, for instance, suggests that what we call point particles might actually be tiny vibrating strings with a length on the order of the Planck length, roughly 10 to the negative 35 meters. That is 17 orders of magnitude smaller than the current experimental limit on the electron's size. If string theory is correct, the electron has a size, but it is so fantastically small that no currently conceivable experiment could detect it. Other theoretical approaches, such as loop quantum gravity, suggest that space itself might have a discrete structure at the Planck scale, which could impose a natural minimum size on everything, including particles. Still other proposals suggest entirely different kinds of substructure that might exist at scales we have not yet probed. The honest scientific position is this. We know the electron is point-like down to roughly 10 to the negative 18 meters. Below that, we do not know. The electron might be a true mathematical point with exactly zero spatial extent. It might be a tiny string vibrating at the Planck scale. It might be something else entirely that we have not yet imagined. What we do know, with certainty, is that whatever the electron's ultimate nature turns out to be, its mass does not require it to have a conventional physical size. The Higgs mechanism gives it rest mass through a field interaction that is entirely independent of geometry. This is a subtle but critical distinction. Physicists are not claiming that the electron is definitely a zero-dimensional mathematical point in the deepest possible sense. They are claiming that no experiment has found evidence of size, that the standard model describes the electron as point-like, and that this description works with extraordinary precision. Whether the electron is truly a point or merely appears point-like because its actual size lies far below our experimental reach is an open question. But the resolution of that question does not change the answer to our central puzzle. Even if the electron turns out to have some incredibly tiny extent, its mass still comes from the Higgs field coupling, not from material packed into that volume. Mass and size remain independent, regardless of the electron's ultimate structure. There is another misconception I want to address head-on. Some people, when they learn that mass comes from the Higgs field and from energy rather than from physical material, conclude that mass must be an illusion, that matter is somehow fake, that everything is just smoke and mirrors. This is completely wrong. Mass is real. It is as real as anything in physics. When the electron interacts with the Higgs field and acquires rest mass, that mass has every physical consequence that mass has always had. It resists acceleration. It generates a gravitational field. It curves space-time. It determines the electron's energy at rest. It governs how electrons orbit nuclei, how atoms form, how chemistry works, how materials behave, how your body functions. The mass is not an illusion in any sense of the word. It is a genuine physical property with measurable consequences. What has changed is our understanding of what mass is at a fundamental level. Mass is not a primitive, irreducible substance. Mass is a consequence of field interactions and energy, but consequences are not illusions. The warmth you feel from a fire is a consequence of molecular motion, not a substance unto itself. That does not make warmth an illusion. The colors you see are consequences of how light of different wavelengths interacts with your eyes and brain. That does not make colors illusions. Mass being a consequence of the Higgs mechanism and strong force energy does not make mass an illusion. It makes mass something we understand more deeply than before. And this deeper understanding reveals something profound about the nature of reality. The world you experience, the solid, heavy, material world of rocks and water and mountains and your own body, is not built from tiny pieces of ultimate stuff. It is built from quantum fields and their interactions. The fields are the fundamental reality. Particles are excitations of those fields. Mass is a property generated by how those fields interact with one another. The solidity you feel when you press your hand against a table is not the solidity of irreducible material. It is the electromagnetic repulsion between the electron fields in your hand and the electron fields in the table. The weight you feel when you hold a stone is not the weight of fundamental substance. It is the gravitational effect of energy stored in quantum fields inside the protons and neutrons of the stone's atoms. This is not a reduction of reality to something less real. If anything, it is an elevation. Reality is richer and stranger and more beautiful than the naive picture of tiny billiard balls bouncing around in a void. The quantum field picture reveals a universe that is dynamic, interconnected, and deeply unified. Every particle is a ripple in a field that fills all of space. Every mass is a consequence of how fields talk to each other. Every force is carried by field excitations. The boundaries between matter and energy, between particles and forces, between substance and emptiness, all dissolve at the fundamental level. What remains is a web of interacting quantum fields, and everything we see, from electrons to galaxies, emerges from the patterns and excitations of that web. The question we started with, how can a particle have mass without having size, seemed paradoxical only because we were carrying the wrong mental picture. We were imagining particles as tiny objects and mass as the weight of their material content. When you drop that picture and replace it with the correct one, particles as field excitations and mass as a field interaction property, the paradox disappears. There is no contradiction. There never was. A particle can resist acceleration without having a measurable radius, because resistance to acceleration does not come from physical bulk. It comes from how the particle's quantum field couples to the Higgs field, and from the energy stored in the fields that compose it. And this understanding applies to you. You are made of atoms. Those atoms are made of electrons orbiting nuclei. The electrons get their mass from the Higgs field. The nuclei are made of protons and neutrons, composite particles whose mass is 99% energy from the strong nuclear force. The quarks inside those protons and neutrons get their tiny rest masses from the Higgs field. The gluons binding those quarks carry enormous field energy that manifests as mass. At every level, your mass comes from field interactions and energy, not from irreducible pieces of ultimate material. You are not made of stuff in the way you always imagined. You are made of fields. You are a pattern of excitations in quantum fields, held together by the interactions between those fields, given mass by the Higgs mechanism and the strong nuclear force, stabilized by electromagnetism, and shaped by billions of years of cosmic and biological evolution. And there is nothing less real about that than the old picture of solid material. In fact, it is far more wonderful. The next time you pick up a heavy object and feel its weight in your hand, remember what you now know. That weight is not the heft of tiny, solid pieces packed into a volume. That weight is energy. It is the energy of gluon fields raging inside protons and neutrons. It is the inertia generated by quark fields coupling to the Higgs field. It is mass, real and measurable and consequential, arising from the relationships between invisible quantum fields that fill every point in space. The object you hold is heavy, not because it is full of material, but because the fields that compose it interact in ways that resist your push. And those fields, the true foundations of everything, do not require size or volume or a tiny container to hold them. They simply are. They fill all of space. They always have. And the mass they generate the mass that makes up your body, your world, and every star in the sky, is as real as anything has ever been. It is just not what you thought it was. That is perhaps the deepest lesson here. Not that mass is fake, not that reality is less than it appears, but that reality is different from what we assumed, and different in a way that is more remarkable, not less. For thousands of years, humans believed that heaviness required substance, that weight demanded material, that mass meant stuff packed into space. And then, at the very bottom of nature, we discovered that the universe does not work that way at all. Mass comes from fields and their interactions. It comes from energy and its many forms. It comes from the relationships between invisible entities that permeate every corner of existence. The universe built everything we see, every rock, every ocean, every star, every living creature, out of invisible fields and the patterns they form. And somehow, from those immaterial, sizeless foundations, it made weight. It made substance. It made you. And the fundamental particles at the bottom of it all, the electrons and quarks and gluons, carry their masses while presenting no detectable size to the most powerful instruments humanity has ever built. They are point-like, as far as we can tell. They might be points. They might be something even stranger. But whatever they are, they have taught us something remarkable about the universe. Mass does not require size. Mass requires fields. Mass requires interactions. Mass requires energy. And in a universe built entirely from quantum fields and their couplings, that is more than enough.